Again, I came with the study of capacitance for you. How can we find out the capacitance for a different type of material? Okay. So here we will take the first of all, we will take is capacitance of a spherical, that means but isolated capacitor. We are going to find out capacitance of an isolated capacitor. Means what? Here only one sphere is there. Okay. And on this sphere we have distributed a charge Q. Is it clear? We have distributed a charge Q. If it is hollow, then the charge will be on the surface. If it is solid, then the whole the sphere will consist of what? The charges. Is it clear? However, this charge Q is always located, always concentrated towards the center of the sphere. Center of the sphere, it is the Q. Okay. Now, if you want to find out, whenever we are going to find out capacitance, we need what? We know the formula C is equal to Q by V. So we need first what? First of all, we need charge Q. And second one, we need potential. So for that, we have taken a point P on the surface of the conductor, which is at a distance of R from the center of the sphere, where we want to find out electric potential. And we know that according to formula for potential, V equal to how much? 1 by 4 pi epsilon naught Q by R. Again, C equal to how much? Q by V. So what is the result? Therefore, C is equal to Q divided by this value, 1 by 4 pi epsilon naught Q by R. This Q and Q will cancel out and we'll get what? C equal to 4 pi epsilon naught R. Is it clear? From there we can say in the SI system C equal to how much? 1 by only 4 pi epsilon naught R. And the value of 1 by 4 pi epsilon naught is equal to how much? 9 into 10 to the power 9. So 4 pi epsilon naught equal to 1 by 9 into 10 to the power 9. Is it clear? So we can say that the value of C as what? C is equal to 1 by 9 into 10 to the power 9 into R. And in general, what this thing is constant, so we can say that capacitance is directly proportional to the radius of the conductor. It means what? If the sphere has a big, if it is a big sphere, then capacitance will be more. If it is a small sphere, the capacitance will be less. Is it clear? From there, what we come to conclude that generally capacitance of a isolated spherical capacitor depends upon the radius of the conductor. Is it clear or not? Is it clear? Just go through it one. Is it clear? V equal to 1 by 4 pi epsilon naught Q by R. Since C is equal to Q by V, we have put the value of V as 1 by 4 pi epsilon naught Q by R. This 2 Q has cancel out and we'll get what? C is equal to 4 pi epsilon naught R. It implies what? 1 by 4 pi epsilon. And as we know, 1 by 4 pi epsilon is equal to 9 into 10 to the power 9. So 4 pi epsilon naught equal to 1 by 9 into 10 to the power 9. And the result is what? C is equal to R by 9 into 10 to the power 9. And from there we come to conclude that C is directly proportional to the radius of the sphere. This is about your capacitance of an isolated spherical conductor or spherical capacitance of an isolated capacitor. Clear? And dear friends, do you know an isolated spherical capacitor, the name of an isolated spherical capacitance? Now you cannot guess it, but I am saying you, after that you will be sure that an isolated capacitor is always with R. Without it we cannot live. And it is that isolated capacitor is our R. Big R is an isolated capacitor here. It is a big conductor of negative charges. Clear? So we are going to find out what is the capacitance of R. That means what? That isolated capacitor R. We know capacitance of an isolated spherical capacitor is given by how much? C equal to R by 9 into 10 to the power 9. Is it clear? And radius for R. Here radius for R is how much? 6.4 into 10 to the power 6 meter. Is it clear? For Earth, the radius is 6.4 into 10 to the power 6 meter. Therefore, C equal to, we will put the value of 6.4 into 10 to the power 6 divided by 9 into 10 to the power 9. And the result is 0.711 into 10 to the power minus 3 farad. So we will get the value of 711 microfarad. Can you imagine? A big type, what a big radius we have. Our Earth is 6.4 into 10 to the power 6 meter. But its capacitance is only 711 microfarad, not a farad. So we can say that 1 farad is a very big quantity. Is it clear? 1 farad is a very big quantity. But we are practically using 50 microfarad, 20 microfarad, how it is possible. So we will later on we will discuss it. But you should know that capacitance of Earth is only 711 microfarad. Clear? This is about your what? Capacitance of isolated capacitor. That means an example of isolated capacitor is our Earth. That is the capacitance of Earth. Is it clear? Now let us find out the radius of a sphere whose capacitance is 1 farad. We are going to find out radius of a sphere whose capacitance is 1 farad. We know for a sphere, C equal to how much? R by 9 into 10 to the power 9. We know it. Implies R equal to how much? 9 into 10 to the power 9 into C. If capacitance is 1 farad, then C equal to how much? 1. So if you put the value of 1, the result will be how much? 9 into 10 to the power 9 meter. It means R equal to 9 into 10 to the power 6 kilometer. So if a body having the capacitance, spherical body, isolated spherical capacitor there, if we want to make a isolated capacitor of 1 farad, we need the sphere of radius how much? 9 into 10 to the power 6 kilometer. Is it clear? If we want to make a sphere isolated capacitor of 1 farad, we need a sphere of radius how much? 9 into 10 to the power 6 kilometer. So big it is. We cannot imagine it's to make a such type of capacitor. That is the what demerits of what? Making and considering an isolated spherical capacitor. We cannot make an isolated capacitor of what? Of a spherical one. Is it clear? Clear or not? All the above things, all the last discussion, from all the last discussion we come to conclude that we cannot make an isolated spherical capacitor. So we are moving towards what? Parallel plate spherical capacitor. Is it clear? And what is the main role of a capacitor? To store the charges. Is it clear? To store the charges. For that reason, what is the principle of capacitor? Let's go through a theory and examples for it. Suppose we have taken a conductor having where maximum numbers of positive charges are there. It is clear. Its name is suppose its name is R. Okay, name is R, where we have taken a positive charge of positive plate. And we place it, we bring a uncharged conductor near this positive plate. What will happen? This side will be a negative and this side will be positive. Is it clear? That means what? As this is a positive plate, so this negative will what? Here it will try to take this positive to that means, but somehow its number of charges will decrease. That means that we can supply some amount of charges to it. Okay. And now what we have done, we have taken we have arc it. We have arc in the system. Is it clear? We have arc in the system. Then what will happen? All the positive charge will come here and this will what? Contain, this will become a totally negative charge. And we know that capacitor is equal to how much? Capacitor is equal to you see one thing, capacitor is equal to charge by potential. As we are bringing all the negative charges here, we are decreasing the potential of the system. And as the potential of the system decreases, means what capacitance of the capacitor increases. So this is the principle. We have to bring a positive plate here, and with it we have bring an uncharged conductor here. What will happen? This side become negative and other side become positive. So now what will happen? The potentiality of the system decreases, and we as the potentiality decreases, means what V decreases, we can to increase the potentiality, what we have done, we can give some charges here. Is it clear? Now when you earth it, then all the charges, all the positive charges will go towards that, because earth is a negative charge, hold a big conductor of negative charge. So this system totally becomes negative. Then what will happen? Here the potential decreases more. As the potential decreases more, the capacitance of the capacitor increases more. So this is the basic principle of what? Parallel plate capacitor. Is it clear? Generally we will study about the parallel plate capacitor, and it is very important. It has a lot of use are there. Is it clear? Without parallel plate capacitor, we cannot think, we cannot imagine our day-to-day life, because everywhere, whenever you are going to see all the electrical equipment, you will see that without capacitor nothing is there. And main electrical capacitor is mainly used by whom? By the mainly which capacitor using we are using parallel plate capacitor. Clear or not? So this is about your principle of parallel plate capacitor. Clear? Okay friends, you were giving two drawings are there, A and B. Okay, two drawings are there. Remember this, whenever you are drawing capacitor, the lines, that area should be what same, their lines should be same. Okay, that means what? They have the same area of cross section. Okay, and this and these are also represented. Both are A and B, representing capacitors. Okay, and this is known as fixed capacitor. This capacitor is a fixed capacitor, and this capacitance is a variable capacitor. If some error is given in the diagram, then you can say it is a variable capacitor. And if it is no error there, then you can say it is a fixed capacitor or non-variable capacitor. Is it clear? So we can represent the parallel plate capacitor by two ways. One is known as what? One is fixed capacitor, when the value of capacitance is fixed here, and another one is what? Variable capacitor. So it is denoted by as arrow. Here there is no arrow. So this is all about your types of capacitor, types of parallel plate capacitor. And now we are going to find out capacitance of a parallel plate capacitor. Again I am repeating, capacitance of a parallel plate capacitor. We know the formula, we know the what principle of this parallel plate capacitor. What we do, we will take a positive plate and we bring a uncharged conductor near it, and when we arc it, it will be what? This potential decreases, so the capacitance of the system increases, because capacitance equal to how much? Charge by potential. Clear or not? And so for that reason, let us take a positive plate here named as X, and another uncharged conductor here which is R10 at a distance D named as Y. Clear? Now the electric field will always directed from positive to negative, field is directed from X to Y. Is it clear? At a distance D. Is it clear? Now we know the electric field between a positive plate and a negative plate. We know that if sigma is the charge density, both are having the same charge density, then we know what? E equal to electric field between X and Y is what? E equal to sigma by epsilon naught. We know it now. We have already derived in the Gauss laws chapter. Is it clear? Electric field intensity between any two positive and any two points. That is, if a plate, any two plates, if a plate is positive and another one is negative, and having the same charge density, then E equal to sigma by epsilon naught. Okay. Now what is sigma? Sigma is the surface charge density. So sigma, since sigma equal to charge by area, so we can say that E equal to Q by epsilon naught A. We can put the value of sigma as Q by A. Is it clear? Now again we know that electric intensity is what? General formula of electric intensity is potential by distance. So from there, what is the formula for potential? Potential equal to V equal to E into D. So we put the value of E as what? Q by epsilon naught A. Q by epsilon naught A into D. Is it clear? Since C equal to Q by V, so we can write what? Q divided by QD divided by epsilon naught A. So we got the value what? Epsilon naught A divided by D. From there, what we can say that capacitance is directly proportional to what? Parallel plate capacitance of a parallel plate capacitance is directly proportional to the area of the plate, area of the capacitor, and inversely proportional to the distance between the two plates. Is it clear? From there, what we can say, the electrical